Hello. So the first speaker we have this afternoon is actually going to be a pair of speakers. We have Elisabeth Meyer from the Leibniz Supercomputer Center in Munich, from the Virtual Reality and Visualization team, and Professor Peter Coveney, who's the director of the Center for Computational Science at UCL, who are going to be talking about some of the work they've done with HemeLB as like a blood flow modeling code. So I'll pass it over to you, Elisabeth, I think.
Thank you so much for the introduction. So welcome to everyone to our talk today regarding visualizing human scale blood flow simulations on the LRZ SuperMUC-NG using Intel's OSPRay Studio. I'm Elisabeth Meyer. As mentioned, I work at the Leibniz Supercomputing Center in the field of virtual reality and visualization. We have a center for virtual reality and visualization here in Munich. And in our team, we also have representatives from UCL, Intel, and experts in the field of biomedicine. So this project, or what I will be talking about, is a collaboration of various projects and institutes. At the very top, we have CompBiomed Focus, which of course focuses on the use and the development of computational methods for biomedicine. It is an EU project. And one of the projects of CompBiomed is HemeLB, which we will be getting into detail later on. And as mentioned, we have Intel in this workflow, UCL, and myself as the LRZ, not only with our supercomputer, but also with our Center for Virtual Reality and Visualization. What do we have planned for this talk? So first, we will give a brief introduction to the virtual human. Peter Coveney will be taking over that part. Then we will go on to HemeLB. What is HemeLB? Then I will be introducing the Leibniz Supercomputing Center, our background with these kinds of projects. Then I will be introducing the center where I work. And then we will be moving on to the visualization using OSPRay. And last but not least, I will be discussing what we plan for the future. Without further ado, we will be moving on to the virtual human.
Elisabeth, thank you very much. And I'm relying on you to advance the slides. It's a big one with various videos in it. The slide here is what is the virtual human? And really, this is an organizing principle for the future of medicine. And actually, one of the things for those of us who are listening to this, who understand the UK initiative and the role of high-performance computing in scientific research in the UK, is that it's still terribly badly skewed towards the physical sciences, engineering in the narrower sense. And we don't see anywhere enough involvement from the biological or the medical end. But for various reasons, in the context of EU space and funding, they've set up large high-performance computing centers of excellence in many strategic areas. And then one of them is biomedicine. So this is kind of the medical answer to all the wonderful talks we're probably going to hear shortly on things that are more familiar in physical sciences, astronomy, cosmology, molecules in chemistry, and so on. This is about how we use supercomputers, and in particular here, visualizing the output of them as a kind of grand challenge for the future of medicine. So the virtual human is the concept, but which is at the heart of this. And it's really about the notion, actually sort of German term I use, as a digital doppelganger or digital twin for any individual. It's not just Joe Bloggs or some average person. It's built on the data for an individual. And it can be used in the scenarios we're looking at all scales, from the genomic to the whole human, indeed beyond, when we're dealing with pandemics and epidemiology. But so it's a huge task to do this. And this picture is just showing you the physiological scale at which we're operating and what is relevant to the talk today in the visualization. This is all about largely organ systems, how we can model and simulate them with high fidelity. We need very powerful supercomputers to do this, but then to wrestle with the data that's coming off it and visualizing it. There's all manner of organs here, and there's the cardiovascular system, which is in many ways central with the heart and the blood flow around it. And the way we proceed here is like a software massive software engineering project. We want to develop the components of this anatomy and then bolt them together. So in this presentation, we're really just looking at the whole, the attempt to capture by imaging the geometry of the whole human vasculature, including the arteries and veins, and see how blood flow goes between them, how fast we can do them, how close are we to being able to do this sort of in, quote, real time, and indeed in an actionable way to advise clinicians, as is said on this slide, of things they might do in terms of interventions and help people, including patients, understand the impact of their treatment. We've got a film on this, it's only 5 minutes long, which I commend to you if you have a chance to look at it. It's on YouTube and it's called Virtual Humans. Let's go to the next slide here. I've talked about this before. I think I did this with our working group about 6 months ago, and probably in the context of uncertainty quantification, which is obviously important for using computers to predict things that are going to be decision making in the context of medical scenarios. So we have to have very powerful codes for this, and HemeLB is the one that's really emerged. It's a flagship code that's used in the UK COMES High-End Computing Consortium as well. So I've talked about it before, and I don't need to spend too much time on it. I'm just going to go over it. Let's have the next slide to look at what's in there. It's a full 3D lattice-Boltzmann code, C++, initially with just kind of standard MPI parallelism, optimized for sparse geometries of the sort we encounter in vascular networks. It's been applied to a range of more specific applications in the medical area, which lend themselves to devices and device optimization and so on and so forth. In the struggle to deal with ever increasing sizes of data and the human, virtual human, we are wrestling with big data. We're wrestling with the need to accelerate the code. So we now have a GPU version of this code that's running at a pretty big scale. Let's go to the next slide to get an idea of what I mean by the scales involved. This is, again, referring to where Elisabeth is from at Leibniz Rechenzentrum in Garching. This machine is at one point was the fastest one in the EU, and it's an Intel-based Lenovo system, which has an interesting island kind of structure or architecture, but basically of the order of 310,000 cores on it when it comes down to it. And this HemeLB code does scale extremely well on that. So the monolithic single instance running on this machine does scale, to of the order of 80% up to a very, very large fraction of the machine. And the tapering off you might see with the green dots on the right is the type of thing you always get when to sustain the scaling at that level, you typically need even bigger data sets. And one of the problems in the design of these mammoth machines, of course, is people might have forgotten that we need to move data onto and off them and to visualize, which is where the main part of this talk is coming from. We do have coupled versions of this, because in the work we're referring to here, you'll see it's actually a combination of the arteries coupled to the veins. Those are two separate instances of a mammoth HemeLB connected together by a model of the vascular network. And then you're dealing with a coupled model. And the coupling is more challenging to deal with in a scalable way. But right now we've managed to get that up to around 100,000 cores for the two things running together. So the next slide, I think, just shows what we're looking at. You've got to imagine on the right-hand side that whole human patient-specific image of the arteries and veins. We do have work to connect it to the heart, but I'm not talking about that now. The size to get good resolution of the blood flow in terms of lattice sites in the model. Currently, it's around 10 billion to 50 billion lattice sites. And as the machines get larger, the code is so scalable, we see no reason why we won't be able to continue to operate it at those scales. So as I keep emphasizing implicitly, if not explicitly here, the quantity of data that we're trying to deal with and visualizing it are big challenges. From the clinician's point of view, and this is the issue, the weakness of using these methods in the medical areas, they're not, our end users are not trained sort of theoreticians or modelers, we need to give them very clear and intuitive visualizations, and we like them to be, as far as possible, sort of interactive. You can see dynamics in them. So I think the next slide may be the last one here. This is the particular application that we're looking at in this work. There's no time or need to dwell on it from a medical point of view, other than to say that it's trying to do modeling and simulation in the way described to advise clinicians ahead of time in the case of a procedure called hemodialysis, where you connect a major artery and a vein, and that's through something called an arteriovenous fistula, which is built and simulated in HemeLB, and it therefore bypasses the vascular beds, I think I mentioned earlier, so that the flow through the vein is enhanced. So what we're doing from the simulation is providing high resolution flow data to our colleagues like Elisabeth at LRZ, and there's some data on it, the size of the data, and the total output per time step, which is, you know, around 7 to 8 bits per output step. And I think that might be your cue, Elisabeth, to take over the talk.
Yes, so as mentioned, these enormous data sets needed to find a way to be visualized, and that's where the LRZ stepped in. I will be giving a short introduction to the LRZ. We don't only do HPC. The LRZ offers a multitude of services ranging from networking to archiving to the Center of Virtual Reality and Visualization. We also do cloud computing and an email service as well. However, our HPC resources are focused on certain application groups such as astrophysics, biophysics, and geophysics. These application groups closely monitor projects and offer code optimization. Our HPC resources also offer general purpose visualization software. So I'm talking about Visit and ParaView. We encourage exploratory science visualization, not only on our servers, but also on our supercomputer as well. And last but not least, we also have the V2C, which I will get into detail later. So our heart piece, also behind me in my background, our SuperMUC-NG. We were a couple of years ago number 9 in total. Now I think we're at place 15. We do have Intel processors in our SuperMUC-NG, but place 15 is, it's time for something new. So what can I say about the phase 2? Unfortunately, I cannot say too much, but what I can say is we're looking at 240 new nodes. We're talking about Xeon Sapphire Rapids as processors, as well as the newest GPUs, the Ponte Vecchio, which are focused on exascale as well as AI. We plan on having our phase 2 up and running end of 2022. So please look forward to that. So what did we as a team, as this team with this workflow do on our SuperMUC-NG before we got our biomedical data? So as a team, we've had experience of running the world's largest turbulence simulation. Here is a short teaser. So with this project, we were testing the limits of certain simulations. We did get a nomination for the Supercomputing Showcase for Data Visualization. You can check out the video on our YouTube page. But with this project, we did hit certain limitations because it is using the SuperMUC. It is, however, using OSPRay, the OSPRay renderer through Visit. So it is scalable, but only on non-accelerated HPC resources and systems. We could switch between interactive graphical user interface and the batch rendering option, and we could cross code. So all in all, the project was a big success. The nomination, as mentioned, for Scientific Visualization and Data Analytics Showcase. And we were on the title of the Inside magazine in autumn 2019. And in the latest Inside magazine, you can also see development of that project specifically. Now to myself and to the Virtual Reality and Visualization Center. For us, visualization means we enhance the display of complex data sets. In easier terms, we make complex information more understandable for the human eye. So we highlight certain information contained in the data sets. And for us, virtual reality means we put the users in the center of the application. The user has a chance to interact with the data set. And by interact with the data set, we're also talking about a certain real-time aspect. And at our center, we do offer three-dimensional displays. So for us, VR also means three-dimensional. As mentioned, we have state-of-the-art hardware. Here on the right, you can see an example. But we don't just offer the hardware, we also offer custom software solutions. We have a team of visualization experts as well as researchers, and we are equipped with these very special virtual reality installations. Here on the right, you can see a projector-based system known as the Cave, which synchronizes over 10 computers and displays the virtual world in this cube, as you can see. We don't just have these projector-based systems. As of a couple of years ago, we do have a LED-based power wall. It goes in the direction of virtual production. So we do also experiment with newer technology. But we also have standard VR hardware and experience in standard VR hardware, so for head-mounted displays and other output devices. So we are part of the Leibniz Supercomputing Center, so we do tend to work with very large data sets. We were also part of the Virtual Human Project a couple of years ago, where a blood flow simulation of the Circle of Willis was done. Then we, of course, had the experience with the Astrophysics project, which I showed previously. So the world's largest turbulence simulation is an astrophysics project. And here on the right, I have an example for geophysics, where you can see convection flows under the Earth's mantle. For us, a goal is always to create photorealistic renderings, as well as photorealistic rendering workflows. So for various projects, we can apply our workflow. And our goal here was to create a 360-degree 3D experience with the data that we received. In our personal interest, we wanted it to be web-based for the point of science communication. How do we reach as many people as possible? And we've discovered how powerful a browser can be, and WebVR in this case. So enough to the background. On to the project itself, visualizing HemeLB with OSPRay. The basis, as mentioned, we have HemeLB with their challenging or with large data sets. We have the LRZ with our SuperMUC-NG, our science mentors, and our focus on virtual reality and visualization. Then we have Intel, of course, with their one API rendering for Xeon, and in this case, OSPRay. So we use OSPRay Studio on the SuperMUC-NG. We have a custom plugin that loads the HemeLB data as is, foregoing the need for preparation. OSPRay Studio offers a 360-degree camera, which is vital for immersive 360-degree 3D images and videos and experiences. OSPRay Studio also offers the option to animate, as well as read animations and tracking shots. And our preliminary results, as we currently are, we can choose between batch rendering and interactive rendering workflows. We can create 360-degree 3D images and videos for immersive experiences. And our next step would be to standardize the workflow for other users. We are running on a development branch of the One API rendering toolkit. Our plugin loads the data directly into the volume kernel library of Intel. And we do have various OSPRay Studio synergies, such as the GLTFs, so we can read GLTFs and animations. We can access the open image denoising, as well as use our GPUs, which we have on our supercomputer, and various renderers, which I will be introducing in the next slide. So that is OSPRay Studio on the SuperMUC-NG. So the various renders that we can use, here are 3 examples. On the top right, we have a path tracer with which we can access different lighting. So we are not limited to certain lighting. We can expand that through spotlights, through HDRI lights. I have an example later in the slides. On the bottom left, we have the Cyvers. a ray tracer, a very efficient ray tracer. And if the CIVIS isn't efficient enough, you can always use the AO renderer or the ambient occlusion renderer, which is a subset of the CIVIS renderer. So how do we go about visualizing the HemeLB data? So first, the preparation would be to get it started on SuperMUC-NG. We use our plugin to load the data. So in this case, we load a snapshot. Then you will see an exploration of the data, as well as the various camera settings we have access to thanks to OSPRay Studio. And at the end, we can, of course, export our output files and, what is very practical, save our scene so we can come back to a later date and have the same settings as we had set previously. So here, a little video. You can see after loading the data set, this is all in real time. So this is one snapshot of the arm that we talked about earlier. And here you can see, for example, how to change the transfer function just to up the opacity of the data set, make it more visible. And you can see I can very simply change the background color to make the entire data set a little bit more readable. And I can explore by simple mouse drags. So as mentioned, this is real time running on the SuperMUC-NG. Here you can see the different render options. So right now is the CIVIS. Here is the path tracer. And here is the AO renderer. So depending on your needs, you can select one of the renderers. Personally, we used the path tracer with a black background just to make the data more readable. And one of the other functions which we use very often is to change the lighting. Here you can see the use of an HDRI or a high definition range image. In this case, it was a simple studio lighting setup. You also have the option to hide your HDRI or your background. The lighting is still the same and up the intensity a bit. And last but not least, the camera settings, which I mentioned earlier. You don't only have access to position and rotation of your camera. Here I have an example of using the depth of field to focus, in this case, on the artery, which is the gray form you can see in the center of the arm. Adjustments, of course, need to be made respectively. So there, the focus is now set on the artery. And of course, at the end, you export your output files, in this case, PNGs and JPEGs, which I have also brought along. So here you have a view of the entire data set using OSPRay Studio. You can see the arm itself, the beginning of the thumb, and here the hand. You can very clearly see in the gray, the artery, and then the veins. And in the veins, we displayed the pressure. So you can see the change in color here. Here I have a view from inside the data set where you can see the use of the depth of field to focus on this strand with very high pressure. So in summary, with our workflow, which we have developed, we can efficiently interact with and explore the large data coming from HemeLB. We can very efficiently and quickly change settings as need be, as you saw with the transfer function. We have the option to animate cameras, and we can always choose between the graphical user interface and the batch rendering option. And this workflow is highly scalable if we're looking at phase 2 as well. And what does the future hold? So in the future, we do want to formalize this workflow. We want to expand our visualizations to 3D, 360-degree images right now we have the 360-degree images, and by doing so, we will have 2D images, 2D videos, 2D 360 images and videos. We will also have then the 3D option, and by doing so, we have basically covered everything from 2D to VR. And as mentioned, we do want to create a web-based experience. I have an example here for a non-immersive 360 panorama, which a user can interact with. So by simple mouse drags, you can have a look around. And this would run in a browser. It can actually run in a browser, just as one example. And last but not least, not only formalizing our workflow, but we want to expand this workflow for other data sets, other research fields such as astrophysics, geophysics, and biology. And if you have any questions, please let me know.
Thank you, Elisabeth. So, and Peter. So, nobody, I don't think, has actually typed any questions in the question and answer. Oh, Sean has just put one in now, so we can have a look at that. What was the total input data volume involved, and what advantages did OSPRay offer over other rendering engines like Blender or Chaos?
Well, currently we haven't tested the limits, so we're just expanding as we speak. And otherwise, we haven't done a direct comparison, but we plan to do so in the future.
Okay, so I was wondering a couple of things. I mean, how, from your description of it, I was just wondering, the end users here, maybe, you know, medical staff or something who, as you mentioned, are not that well trained in visualization. And how do you envisage that working? Is it they expected to come into the computation center and have some technicians who will guide them, or is it more likely that they'll be using the web VR type interface, and does that require also some sort of technical support at the same time?
That is a very good question. So as a visualization expert, I see my task as bridging the gap between the end users as well as the experts in the respective fields. So my job would be to work together with the experts to be able to select certain images and videos that are of relevance to the end user. In our case, with the static 360-degree images, what is the point of interest? What do we want to convey to the end user? So in the web-based application, the end user would be able to very intuitively with a mouse look around their own axis. And we look to expand that, as mentioned, with 360 3D, so they can look at it in a headset as well as on the smartphone, so they can have a look at it.
Yeah, because I suppose it's very relevant at the moment with nobody can really come into your center, I suppose.
Yes.
Can I ask a question?
Yeah.
Sorry, because as a panelist, unfortunately, I can't put it in the Q&A box. So thanks very much, Elisabeth. Thanks, Peter. It was really interesting. So the problems that you showed, Elisabeth, were they all steady state, or was there a time dependency in the data?
Okay, so the data that we're now working with is simulated, but we can import, we currently have like one heartbeat, and we can import that heartbeat. So it is not completely static, but the snapshot I showed was static.
Okay, we had quite a few talks yesterday about streaming data and the idea that at exascale it may be necessary to compress data, to put error bounds on it. So I was wondering with these techniques, do you have concerns at extreme scale, at the speed, can you actually fetch the data fast enough to feed your visualization?
Seeing as
what you showed was quite a small domain.
Seeing as we are currently working with simulated data, not simulating data, it is for me a big difference. So I would make a difference between what we are doing and then visualizing the simulating data.
So what I'm really interested in, and Elisabeth knows that well, is what we're heading towards in this discussion, which is in situ computational steering, which we've done in the past a few times, but now we're talking about it at real scale, so it would be real time. Obviously, we want to be able to render the stuff as it's being done And I suggest, but we need to demonstrate this, that the presence of graphical processing units certainly dramatically accelerate that. They were created for video gaming after all. And that's what we're aiming for here. To answer the earlier question, I would like to have clinicians who are actually able to play a video game and computationally steer a simulation ahead of carrying out an intervention to figure out where they should make the intervention. And they need to be able to do things like that. Now, if you can play video games, my contention is you can do this as well without huge sort of scientific training on visualization. But I think it's feasible to imagine this is going to happen. Do you want to comment on that, Elisabeth?
I definitely agree that that appears where we're heading with this project. We do, of course, look at the next step, which would be to implement it in the browser and make it accessible to various people. A buzzword going around right now is science communication, and offering a very easy way to access these visualizations. But yes, I can see definitely an interest in interacting with the data.
Just a brief question, if I can, Chris, for Peter, actually. Is exascale big enough for a virtual human? I guess because what I had in the back of my mind was some work I've done with colleagues of yours at UCL on high-intensity focused ultrasound, which, because of the very high frequencies, was computationally very demanding. But to make that work, we'd actually also need a full model of the vascular system as well, because that transports heat. If you think about some of these problems, is exascale big enough for a digital twin of a person?
So what we were just talking about there was just a forearm, right? But we published at least one paper on doing the full human coupled model, and the benchmarks you saw that we reported are for the whole human vasculature. So it's possible to do it. The challenge is related to the time scale. So this is a problem I think you're very familiar with, but not everyone is. They think if you can get an application that scales to the full production partition, and however big it is, you've cracked the problem. Clearly you haven't, because the issue is I have to be able to run that thing, sufficiently long to do things that matter to me. But we can definitely scale these problems onto these kinds of machines. I have every confidence we can do that. Then it's being able to essentially run them for long enough. How many heartbeats can we actually perform in a reasonable amount of time? We're nowhere near, of course, real time in the sense of comparison with an actual human at this moment, but we can put some of these things on there. And in the end, it's also, as I was saying about this, do you remember the picture of all those organ systems being bolted together, that it's not necessarily sensible to have the entire production partition running one single thing. You're going to couple a bunch of things like the heart and bits of the arterial tree together. And then you can also easily see how you fill the machine up. And the question remains open, how far can you then answer problems that are, as you're getting at, really interesting? For us, there's no doubt that there are some things that we can only do if we're able to get access to this scale of machine. But you'll always find something you might be interested in, or I am, that will be bigger than the next huge machine that's put in front of us. But that's great, because there's always something more to be done.